So now that we have seen the definition of the transpose of a matrix, as well as an example, I want to explore some of the algebraic properties of the transpose of a matrix. So here we are going to let matrix A and matrix B be size-appropriate matrices such that the following sums and products hold true. So the first property is that the transpose of a matrix A is equal to matrix A. And now we can pretty quickly see this just by thinking about this logically. So this is not a formal proof, but just to help us understand what's going on. So let's say if we have the ith-jth entry of matrix A. So then by taking the transpose, we can see then this is equivalent to the jth entry of the transpose of matrix A. So now if we go ahead and start with that entry, so starting with the jth entry of the transpose of matrix A, and we go ahead and take the transpose again, we can see that then we're going to be left with the ith-jth entry of the transpose of matrix A, which is the same entry as the original matrix A. So these are showing us the equivalence of our first property. Again, that is not a formal proof, but just to give us a little intuition about what's going on. The second property says that if we have the sum of two matrices, say matrix A plus matrix B, and we take the transpose of that sum, that this is equivalent to taking the sum of the transpose of matrix A plus the transpose of matrix B. And this one is pretty obvious that it holds true in both directions because matrix addition requires that the two or more matrices must be size equivalent. So whether we take the sum of the two matrices and then take the transpose is going to be the same as taking the transposes and then taking the sum. And that's again because matrix addition requires the matrices to be size equivalent. So to be size equivalent or the same size. So the order in which we apply the transpose does not matter. The third property says that if we have a scalar multiple, C, times the transpose of matrix A, that's the same thing as taking the scalar multiple C times matrix A and then taking the transpose. And this is true for all scalars C. And again, this one's pretty intuitive simply because C is a scalar. It's a constant. It's not a matrix. So the order in which you multiply by the scalar doesn't matter. We'll get the same answer either way. And last but not least, property 4 says that if we have the product of two matrices, so say if we have the product of matrix A times matrix B, and we take the transpose of that product, that this is equivalent to the product of the transpose of matrix B multiplied by the transpose of matrix A. Now I want to make a little love note here that we have to switch the order to maintain the property of matrix multiplication. So we must switch the order here. To maintain the properties of matrix multiplication. So I'd like to take a minute again and think about an informal verification for this last property. Again, this is not a formal proof, but just to give us a little intuition about what's going on. So let's go ahead and let's suppose that matrix A is an M by N matrix, and we'll suppose that B is an N by P matrix. So we can see that the number of columns of the first matrix match the number of rows of the second matrix, letting us know that the product exists. So we can say that matrix A times matrix B exists and is a M by P matrix. So now that we know the size of the product, we can observe that the transpose of the product of matrix A times matrix B is a P by M matrix. So there is the left-hand side of our property number 4. Now, keeping in mind the size of matrix A and the size of matrix B, let's think about the transposes of these matrices and then the resulting products. So we can note that A transpose, since A is an M by N matrix, A transpose is an N by M matrix. And we can see that since matrix B is an N by P matrix, that the transpose of matrix B is going to be a P by N matrix. So using this, we want to think to ourselves, okay, well, does the transpose of matrix A multiplied by the transpose of matrix B exist? No, this does not exist. We can see that the number of columns of the first matrix does not match the number of rows of the second matrix. So this product cannot exist. Now what about the reverse order? What about if we have the transpose of matrix B multiplied by the transpose of matrix A? Well, in this case, we can see that the number of columns of the first matrix does match the number of rows of the second matrix. So this indicates to us that, yes, this matrix exists and that it's going to be a P by M matrix, which is the same size as the transpose of the product. Woohoo! So again, this is not a formal proof, but helps to provide us with a little intuition for property number 4. And one final concluding thought, another general cautionary piece of advice. And we say that in general, the transpose of the product of matrix A times matrix B does not equal the transpose of matrix A times the transpose of matrix B. And this is even when the transpose of A times the transpose of matrix B exists. So we just want to keep this in mind as we proceed through computation.